So in the two both plots, what you're looking out for is when the magnitude crosses over the 0 dB line, because this comes from 20 log 1. Okay, it's from this one. And I do a 20 log of that value is 0 dB. Okay, and similarly the minus 180 degrees line. And from there we do the calculations to find gain margin and phase margin to conclude about the stability. Okay? So that's the overview, the concept for chapter 4. Of course, the questions are the applications of the concept. Okay? So it can be asked in all kinds of different ways. So we'll be doing more questions in the tutorial and in the practice paper next week as well. Okay? But please bear this whole concept in mind. Okay, I'll put this up on the as well. Okay, with that, I go on to chapter 5. Any questions of this? Chapter 4?
Wow, you blocking. Thanks.
Okay, chapter 5 is the last chapter. Definitely tested, it's not optional. Okay, so it's a short chapter though, but it will come out, okay, definitely in the exam, because there was no other way to test this. It didn't even come out in the quiz. So there will be at least 10 marks of question on chapter 5. At least 10, no? Okay, got any more. So please study, don't just skip this. Okay? So chapter 5 is a very quick introduction to digital control system. Okay? All this while, okay, we never come across this term now, okay, because we have been just looking at mathematics calculation, okay? So what exactly is digital control system? Please pass attendance list around.
I didn't sleep. That's just like common sense.
Yes, please settle down quickly. You can socialize later. Okay, so can I continue? Okay, so why digital control system? Okay, before I even come to digital control system, right, I have to talk about the predecessor. That means what was it before digital control system came about? Okay, historically we have been using analog controller. What have you been looking at in your lab? CA lab so far, what have you been using?
I don't know.
MATLAB. Computer. Okay, computer is definitely digital controller. And MATLAB is simulation. Okay, we are not even dealing with the real control system. Do you all remember lab 1? Okay, already 2019, all erased already. Lab 1, okay, there was one controller board, ancient looking one, a big one on the table where you have to turn knob one, okay? That is analog, okay? That could be as old as you all, okay? That's why after the lab 1, I never show you all anymore already. That was just the intro to show you that how things were before computer came in. So analog is the one that you saw in lab 1, okay? The one with the knob. What is it made of? Okay, it's made up of electrical components. There's a lot of components underneath. It's a big box because there's so many resistors and capacitors and transistors inside. Okay, that is an analog controller. What's the problem with that? Okay, over the years, got wear and tear, your resistor will spoil. Okay, and it also suffers drift. Okay, what it means is that at the installation time, your resistor is 330 ohms. Over the years, it becomes 370 ohms. Okay, for example. So all these are the problems that come with analog components. Any kind of analog system. That's why a lot of systems moving to digital. Okay, and if you want to change the controller, you basically have to change the circuit, which is not easy. Okay, you have to solder, desolder, okay, or send for PCB verification. It's all not easy work. So what happens because of this is, now we move to digital. Okay, digital means we use computer to implement control systems. So that's what is happening in the industry. Okay, and the reason is what I just explained. Okay, because of all the disadvantage that you have with analog controllers and the advantage that comes with digital controllers. Okay, so I've just named a few here. Okay, basically it's easy to change the design. How to change the design in the computer? If you want the computer to change from P controller to PI controller, all you need to do is change the code. Okay, and save the code again. So which is so much easier than doing the circuit again. Okay? So that translates to cost reduction. Now you don't have to buy the parts again and do the circuit again, right? So it's just writing code. Okay? And noise immunity is all the additional programming that you can write to reject the noise. Okay? It all comes together with the algorithm. Okay? So because of this, okay, what we have is this kind of block diagram.
Never happened.
Okay, please listen up. All this theory will be tested on. Chapter 5 questions are mostly theory. Okay? There are very little calculations. So you need to understand why we have digital control.
Today I was going home.
So if you see the block diagram here, I have one big dotted rectangular box. And there are some outside the box. What do you all think is the difference between those inside the box and outside the dotted box?
And
I already have a big solid rectangular box. Why I have one more here? What is inside and what is outside? The part inside the box is the digital part of the control system. Not the whole control system is digital, you know. Okay? The digital part is inside the dotted rectangular box. Okay? The part outside is still analog. Okay? Why is it still analog? Because your motor, your plant is analog one. Okay? It is not digital. First of all, do you all know the difference between digital and analog? Before I go on. What is the simplest difference that you all can tell me? Why all of you all ask this Joel? What happened? Like he just came in to take things like that. Okay, please come back here. You all are very distracted today. I don't know why. What's the key difference between digital and analog? Huh? What? Youngsoon again? What did you say? I didn't catch it. Huh? Can touch? Which one can touch?
You are into the noise.
Okay, never mind. Okay, digital can be only 1, 0. Okay, discrete values. Analog can be continuous value. That's the basic difference you all should know. Okay? When you have a plant, okay, let's say the plant is a motor. Your motor, can it have 1 and 0 going into it? What do you need for a motor to run? You need voltage, right? Okay? You need continuous signal for the motor to continuously spin. Okay? So the rest of the parts, they are all analog. That means these are continuous time signals. Only the part inside the dotted rectangular box are going to be 1, 0. Why? Because we are using digital control system. So when you want to use digital control system, got all these extra things. What is this ADC? This is analog to digital converter. These are all your EDC stuff. I'm not going to go into the details, but you need to know that they are there, okay, as part of the system. Okay, similarly, this is digital to analog converter. Okay? So what's happening here is I have a continuous signal that comes in. Okay, but this continuous signal cannot go to the computer. The computer don't know what to do with it. Okay, so you need to cut the signal up, get the individual values, change the analog value to 1, 0, and what goes in is 1, 0, 1, 1, 1, 0, 0, some signal. Okay, that goes to your computer. Then your computer processes this based on what you want. Okay, this is your input, the set point temperature. And of course, the output also will be 1, 0, 1, 1 something. Okay. So what happens again? Here you need to change back to analog continuous signal before you can send your system to run. So please keep this in mind. Not the whole system can be run by computer. No. Okay, the computer is only the controller part. The rest of the plant is the rest of the system, which includes the plant, the sensor, or all the other components, are going to be analog. Okay? So you definitely need to have all these interface to do the conversion, okay, from analog to digital and digital back to analog. Any questions up to here? This is just the schematic, okay? So let's move into what actually happens when you have the digital to analog conversion. Okay, the first thing that happens, okay, when you do the conversion, okay, is the sampling, okay? So I'll explain this whole chunk paragraph on stop using the diagram
Let's
below.
pick up.
Okay, the signal that I have right on top is an analog signal. Okay, that's what I meant by continuous. That means every moment got some value. There will not be any break in your graph. Okay, it's a continuous graph. That's how the input comes from your sensor. Okay, every moment you measure the temperature, right? Okay, so what happens in the next stage? Sampling and analog to digital conversion. That means at every regular interval, I'm going to look at the graph, take the value. Okay? So what I have here is discretized signal. That means at every regular interval, I have a value. Okay? In between that interval, I don't know what the value is. Okay? That's what we mean by discretized signal. It is not a continuous graph anymore.
Really?
Do you all understand the difference between the first and the second graph? That was my first explanation.
Thanks.
What happens is the same graph. What is happening is every TS, okay, seconds, okay, that is stipulated. Let's say I call it 1 second. So every 1 second I'm going to look up the value and I record down as 1 point. Okay? So after TS I look up again, it's this value. So that's why the point move up. Okay, and so on and so forth. So all these points correspond to the particular value at that time. Okay, and you see they're all equally spaced. So it's always going to be after TS seconds. Okay, this TS is called the sampling period. Okay, that's just a notation to say the number of seconds you must wait for it to lapse before you take the next reading. Okay, so there is two things happening. What I've just explained is just the sampling only. Haven't do the conversion yet. So, for example, let's say this value here is 4.5. Okay, this value here is 6. Okay, 6 here again and 7.5. Okay, all these are random examples. Is this digital already? No. Still analog, right? So I still need to convert this to 101100 some value. Okay, that is the A to D conversion. Okay, what happened from 1 to 2? It is just sampling only. Okay, so please take note, two things happening here. From 1 to 2, getting the points from the graph is sampling. Changing the value from analog to digital is the A to D conversion. So they are both happening at this point. Yeah, I just want to illustrate everything in one picture. I just squeeze it. Okay. Any questions so far? Sorry. The change from graph 1 to graph 2 is sampling. Okay. The second part that's happening is the A to D conversion here from the 7.5 bits. Okay? Okay? So as I said, all these, the details are not going into, but you need to know the overview of what's happening. So once you have the 10 bits, go into the computer think of what should the output be. Then now what happens next is you want it to convert it back to analog. So let's say I change back the same value, okay? I'm just trying to prove a point here. So what I'm going to do is, let's say I have the same point. I want to construct back to continuous signal. So what am I doing from here to here? From the second to the third graph? How do I get the graph? The original point was here. Okay? The next point is here. What I assume is, okay, now since at the start of the time interval I know it's here, I assume that it stays at this point until the next interval. Until I get the next point, then I jump. Okay? Again the same thing, okay, it was here until the next interval where it's also here again, so I continue. Okay? So this method of reconstructing the graph, okay, there is a method called zero order hole. Okay, this is just for your knowledge. I will not ask this in the exam because there's so many ways to reconstruct this from here. Okay, the one I'm saying here is just for illustration purpose, is the simplest. It's called zero order. That means you assume it's the same value all the way. Okay, got other ways where you can assume it will be a slope, okay, from here to here, okay, but we are not going to that. Okay, so I'm assuming the simplest, which is the same constant value until the next interval. So when you see this graph, this is obtained from here based on the points. Okay, so this final graph is called the reconstructed signal. That means I get it back from the discrete graph. Okay, so is graph 3 and graph 1 the same? Would you say they are similar? Somewhat. Okay, so what is lagging? The crucial point would be roller coaster, yeah. All these peak points and the minimum points, which could be very crucial in the control system because you want to know what's the highest overshoot or all those kind of important details are gone. Why? Because it happens in the middle of your sampling. Okay? So this difference between the reconstructed signal and the actual signal is what we call the reconstruction error. Okay? That means every time an analog signal goes into a digital control system, there will be this error, no choice. Okay? The error is that the reconstructed signal is not the actual signal. Okay? There is some loss in precision. Okay? So, if you tell me, Cher, why, if I ask why we move in the digital control system, and your answer is, Cher, it's more accurate. It's definitely not accurate. Okay? Because of this loss in precision. Okay? How do you think you can avoid this? How to make sure I can capture all the green circle? What can I do? Don't tell me go back to analog, but I still want to keep it to digital. What can I do to this TS so that I can capture all the green signal? Smaller, okay? If I make the TS smaller, yes, true enough, I can capture all the important points, okay? What is the problem if TS is smaller? More points. More points means what? More work? Not more work for you, but more work for the computer. It has to store all the points, okay? Which may not be possible when you have a plant that's running 24/7, where you have so many points, okay? How to store all of that data storage, okay? So that's why you need to have a balance. So on the next page, how to avoid the reconstruction error, okay? So basically this is a big problem. Everywhere, the industry also has this problem. You don't want it to be too small, you don't want it to be too big. How to choose the right sampling period, okay? So this whole section here, the parts that I've highlighted must be in your cheat sheet, please. Okay, all these formulas are guiding rules to help you to choose your sampling period, depending on the situation. Okay, so mostly I have 4 main rules that should help you in any kind of situation. So I'll go through the rules and I'll go through questions where you can use the rules as well so that you understand where it applies, okay? So let's look at the first rule, okay? Rule number 1. This one is rule number 1. The rule number 1 comes from Nyquist criterion, okay, but that's irrelevant. What it says is that if you have a repetitive sine wave, okay, sinusoidal signal, it can be completely reconstructed if at least 2 samples per cycle are taken. Okay, so